Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to look at the concept of linear independence. So recall that from the previous video, we talked about the concept of linear combinations and the concept of span. So the concept of linear combination is about reachability. So suppose you have, say, vector v1s, you have another vector v2, and then you have another vector v3. And so the question is, can you do some kind of adjustments to this vector v1 and v2 so that the sum will be the vector v3? So adjustments means that you are either multiplying the vector v1 with a k1 scalar, which means you can extend it. You can multiplying it with a negative number, so you can reverse these directions. So you are playing with this kind of extensions, contractions, change of directions to these opposite directions and extensions, contractions. So you are playing with k1 v1 plus some kind of k2 v2, so that k1 v1 plus k2 v2 will give you this vector v3, so on and so forth. So you are playing with this kind of idea. So this is the concept of reachability. Can you reach vector v3 by linearly combining the vectors v1 and v2 by adjusting and rescaling those vectors v1 and v2. So this is the concept of reachability. So span and linear combination, those are concept of reachability. The concept we want to talk about in this video is the concept of linear independence. That is the concept of redundancy. So suppose you have these three vectors that span a particular vector space. So the question is, can we remove this one of the vectors and we still span the same vector space or not? That is to say that whether or not these three vectors actually are related to each other. Maybe two of this plus one of this equal to this. So I don't really need this, okay? So one of the example I used to mention is like you all have the experience of having to do group works, right? So you do group works, you have three group members, but sometimes one of them is redundant. Remove that person and you still get the same amount of work because this person never contribute. So we want to be able to talk about this kind of concept. We want to be able to identify which vector are dependent on the other vectors, or maybe there are no dependency whatsoever. So that's the concept of linear independence. We want to talk about that in this video, okay? All right, so without further ado, let's get right to it. All right, let's begin by looking at the objective for this video. So at the end of this video, you should know what does it mean to say a vector is linearly independent or not. That's the whole point. And you should also know how to use Wronskians to determine whether a set of vectors is linearly independent or not. All right, let's start by looking at this example. This is an example that we have seen before. We have these vectors, 1, 1, negative 6. And we can see that these vectors can be written as 2 times this vector minus 1 times this vectors. So from the previous video, we say that the vectors 1, 1, negative 6 can be obtained by adjusting this vector right here and this vector right here. In fact, we know how to adjust them. We take 2 times of these vectors and then basically reverse the direction of these vectors and sum it up, right? So the proper terminology is that we are going to say that this vectors 1, 1, negative 6 can be written as a linear combination of this vector right here and this vector right here. Okay, so let's abbreviate all this thing here by saying that this is a vectors w and this is a vectors u and this is a vectors v. So the above equations can be written as w equals to 2 times u minus v. And obviously, our intuitions will tell us that this vectors w is related to the vectors u and v. So the vector w is like depends on the vectors u and v in the sense that your w can be written as a linear combination of u and v. Okay, so we want to make this concepts slightly more precise. So we say that a set of vectors, is linearly dependent, right? If one of them can be written as a linear combination of the others, okay? So because of this, right? So this collection of vectors is now linearly dependent because one of the vectors there can be written as a linear combination of the others. Actually, the example that we have seen here is that w can be written as a linear combination of the other two, but you can also easily rearrange these equations, and you can also say the same thing for the u and for the v. They are all related to each other. All right, so they're all related to each other. All right, so again, we want to make this slightly more precise, so we're going to do one very basic operation. Let's move everything on the right hand side here to the left hand side. So we are going to write this as negative 2u, okay, plus v plus w, okay, equal to the 0 vector. So I'm rewriting this equation to this, okay. So if you look at C1, okay, let's call it C1 times U, okay, C2 times V, okay, C3 times W. Okay, let's look at this equation for a minute. Right, so this one right here, this is our scalar. Okay, this is our scalar, so they are just real numbers. This is our scalar. These are also just real number. Now, this equation, okay, if you are looking for C1, C2, and C3 such that this whole thing here will be equal to 0, these equations, these linear equations, obviously has a solutions. There's a trivial solution for this. So if your C1 is 0, your C2 is 0, your C3 is 0, you obviously will have 0. So every time when you look at an equation like this, you know that there's these equations always have a solution. If you're looking for C1, C2, and C3, there's always C1, C2, C3 that can make this whole thing equal to 0. And the easiest way is this. That's the reason why it is known as the trivial solutions. Okay, but if you look at the same U and the same V and the same W here, we'll see that we actually have non-trivial solutions. So this is our new scalar. This one is a 1 right here. There's a 1 right here. So you can see that if we look at the C1, C2, and C3, if you still call the C1, C2, and C3, you see that our C1, C2, C3 doesn't have to be all 0 anymore. So when you have some kind of dependency and you rewrite your equation like this, you will see that the system, okay, this particular system that looks like this particular system right here, that looks like this. If you look at all the scalar does not have to be all 0, okay? You can have some of them non-zero. In our case, they are all non-zero, but the key thing is they don't have to be this. Okay, they don't have to be all 0 in order to get 0. Okay, so when that happens, we will say that the vector u, v, and w has a relationship in it. They have some kind of relationship in it, so that this equation does not have a trivial solutions. Okay, so let's make this precise. Okay, so I'm going to give you the definition here. Okay, so a set of vectors, right, v1 all the way to vk is linearly dependent. All right, they are linearly dependent if they have relationship among them. If this scalar, okay, at least one of those scalar are non-zero, such that you have this equation equal to 0. Okay, so if you have linear dependency, then if you look at this equation, okay, and you look at all this scalar here, they doesn't have to be all 0. For example, like here, it doesn't have to be all 0. So when that happens, you will say that those vectors here are linearly dependent. They have some kind of relationship when the scalar here are not all 0, and you can still make the 0 vectors. We can also look at this. We can also look at the equivalent definitions for independence. Okay, so they are the same. We are just negating this statement here in order to get this. All right, because when you are not dependent, then you are independent. If you are not independent, you are dependent. Okay, so another definition that we can use, and in fact we use this more often, right? So let's look at this. So a set of vectors, okay, v1 all the way to vk is called linearly independent, okay, which means linearly not dependent if and only if the coefficient for these vectors has to be all 0. So if you set this equation up, okay, and you try to solve for the C1, C2 all the way to CK, and you realize that the only solutions, by the way, as I mentioned, this system always have a solution. But if the only solution is that the trivial solution, all of them have to be 0, that means there's no relationship among all those vectors, so they are linearly independent. If you try to solve for this equation, and you realize that this equation here, you can make a 0 vectors by not necessarily having all this scalar to be 0, then these are dependent. Okay, so this is very important. So let's look at it one more time. Okay, so let me tell you in terms of, we can't understand why this is true from the example above, But let me say how you actually do the computation when the questions ask you whether the set of vectors is independent or not. You always set up this equation. If the questions say, hey, look at these vectors, are they dependent or are they linearly independent? Are they dependent or they are independent? Are they related to each other or they are not related to each other? You don't care. You just set up this equation, okay, and look for the C1, C2, all the way to CK. If all of them has to be zero, then they are independent. If one of them not has to be zero, at least one of them not zero, then we will say that they are dependent. Okay, all right. So negating all zero, okay, means that at least one of them is not zero. So you can see that here they say at least one of this is not zero. Okay, then this is different from this. Okay, so let me say that one more time. If you want to determine whether something is independent or not, always set up these equations. And if your solutions is all zero, they are independent. If at least one of them is not zero, then they are linearly dependent. Okay, they are linearly dependent. All right, and this kind of definition works for all vectors. So again, this is not only for Rn, but it's also for P2. It's also for function space, matrix spaces, and all that kind of stuff. So we will look at it. Okay. All right. Let's look at one example here. So the question is, determine whether the following set of vectors, these two vectors here, are independent or not. Okay. So set up this equation, a constant. You don't have to call it C1. You can call it whatever you want. But this is a scalar. So set up these constants, x of this vectors, y of this vector, set it to 0 because the 0 vector here is this 0 because we are in R2. Okay, and we want to solve for the x and y. Okay, so this is equivalent to this augmented matrix. Rho reduces it, you get this, which means that you have a unique solution. And in fact, the only things that can make this equal to 0, 0 is that your x and y has to be 0. Okay, there's no other choice. How do you know that? Because this is how your REF matrix looks like. So therefore, by definitions, these two vectors are independent. There's no relationship among them whatsoever. Okay, they're independent. All right. Okay, so that's the situation here. All right. So it's pretty easy to implement this kind of computation because if they give you, obviously we are in R3 now, and then they wanted to figure out whether or not these vectors are independent or not. Again, set up these equations. Okay, a scalar, this vector, scalar, vector, scalar, vector, set it to 0. And see whether or not these numbers here, does it have to be all 0 or not? So this system is equivalent to this augmented matrix. You row reduce to this. And you will see that because of this one right here, we have pivot, we have one free variable. Okay, in fact, we can set our z to be our free variable. So you will see that this is not the only solution. We have many other solutions. This is not the only solution. In fact, we can set our z to be free variable. And we can actually pick out one particular example to show that I can take one of these vectors, and minus one of this vector to get 0, 0, 0. So I don't have to be all 0. I can see that I have free variable. I have infinitely many solutions for that. So there's more than one way to write this. Okay, and so they are dependent. So these three vectors, they are dependent. Okay, they are not independent. I mean, as a student, you know, right? When you have assigned a group projects and you have 3 group members, you know, some people just doesn't do work. One of them is, you know, is just redundant. And we can see from here that one of the vectors is redundant. Okay, so here, this one right here, everyone is doing work. They are independent. They are really contributing. This one vector can never be related to another vectors. But this one here, one of them is redundant. Okay, just like one of a group member, you can get rid of that group members and nothing changed. Okay, right. So so as you can see here, we have 3 vectors, but they are related. How are they related? Well, you can see that this is how they are related. Okay, so computationally, it's very straightforward. Computationally, you always set up the equations and solve for the C1, C2, and C3. Here, I'm using X, Y, and Z. You can use any constants that you like. It doesn't really matter. Okay, so basically, to summarize, if you have a vectors, V1 all the way to Vm, if this is all in Rn, so to determine whether or not they are independent or whatever, you basically set this equation up, just like the definitions. You set up this equation, and you will see that it is equivalent to this linear system. You solve them, and if you have non-trivial solutions, okay, then they are dependent. If you only have trivial solutions, then they are independent. So this is just a summary of what we have done. You don't even need to care about this. Just use the definition if you want to, okay? All right, so now we are moving to other types of vectors. So no longer just R2 or R3. So now we are in polynomial of degree at most 2. So we have 3 vectors right here. One of them is 1 plus x. Okay, so another one is x plus x squared. And then another one right here is 1 plus x squared. So the question is the following 3 vectors. Are they independent or are they dependent? All right, so take a look at this problem, and we'll see you later. All right, let's take a moment to think about these problems, and you can pause the video, and when you think you already have the answers, you can restart the video, and we can look at the solutions together, okay? All right, welcome back. So what's your answer? Okay, so let's look at them. You always set up this equation. Okay, as I said, this is your vector now, okay? Even though your vector is polynomial, but you should get past this by now. So conceptually, this shouldn't be a problem. C1 of this vector, C2 of this vector, C3 of this vector, set it to 0. Our 0 here is a 0 polynomial, okay? So this 0 vector here is our 0 polynomial. And so you know that, okay, so 0 polynomial means that you can also write it as 0 plus 0x plus 0x squared. So for polynomial to be equal to this, their coefficient have to matches. So let's look at the constant terms. So if you rewrite them, regroup, okay, grouping all the coefficient for the x, coefficient for the constant, coefficient for the x squared, you get this. So that means that this one here has to be equal to 0. This gives you this equation. This one here have to be 0. This gives you this equation. And this one here have to be 0. And this gives you this equation. Okay, so now let's solve for it. So even though we started with polynomial, but the system we are solving here is a system of equations involving real numbers. Okay, there's no more polynomial. And this one here has an augmented matrix that looks like this. REF gets you all the way to here. And you will see that your C1, C2, C3, they all have to be 0. Pivot, pivot, pivot. So that means that this equations, if you set this up, the only answer for the C1, C2, C3, they all has to be 0. So by definitions, you do not have a choice. These are the 3 linearly independent vectors. So they have no relationship among them. So 1 plus x, x plus x squared, 1 plus x squared are not related. Okay, they are not related. Okay, so that's how you do it. Exactly the same as before, nothing really different. Okay, now, again, changing the vector space to M2 by 2, and I'm asking you now, you are given this matrix, these vectors, right? These vectors right here, these vectors right here. The question is it independent or is it not? Okay, all right. All right, let's take a moment to think about the problem, and you should pause the video. And when you think you have the solutions, you can restart the video and we will look at the solution together, okay? Hello, welcome back. All right, so I hope you have the answers. So what we do is nothing really different. We set up these equations, right? Constants, C1 of this matrix, C2 of this matrix, or you call it the vectors, and set it equal to the 0 vectors. Our 0 vectors is, in this case, this particular 0 vectors. Every vector space has a 0 vectors. In this vector space, our 0 vectors is this. All right, and I'm skipping a lot of steps here, but you should be able to extract a system of linear equations and solve for the C1, C2, and C3, and you will see that your C1, C2, and C3 does not have to be all 0. In fact, I can find a particular C1, which is 1, a particular C2, which is 1, a particular C3, which is -1, so that this whole thing here can still get you to the 0 vectors, which means that this matrix, this vector here, this vector here, this vector here, they are dependent. They are related to each other. And how is their relationship goes? They are actually related in this way. All right. So you will be able to see that in this vector space, okay, in this vector space here, these 3 vectors here are not independent. They are not independent, they are dependent. But by now, you should be able to see that the way we identify whether a set of vectors are independent or dependent, we always do the same thing. We always set up all this equation and try to solve for the C1, C2, C3. So if you look at the previous example here, the polynomial example and so on and so forth, the reason why we can solve C1, C2, and C3 easily is because we can compare their coefficients, right? We can compare the coefficients, for example, right here. You can look at the coefficient for the constant term set equal to 0, coefficient for the x term set equal to 0, coefficients of the x squared term set equal to 0. So you can do all that by comparing coefficient, but sometimes we can't really do that, especially if you're in a function space that looks like this. So if I ask you whether or not this function ex and xex, so this view as the vectors, all right, so are they independent or not? Set it to the 0 vectors. In this case, it's our 0 functions. So put a C1 here, put a C2 here, try to solve for C1, C2, okay? And then you're running out of methods. You can't really do that because it's different from what we have seen so far. Before that, you have polynomial. You can compare their coefficient, but there's no coefficient for an exponential function like this. And also, there's no coefficient for a function that looks like this. So we have to find another methods to solve for the C1 and C2. And the way we do it is to create a system of equations in a very artificial way, and then work from there, right? So this is going to lead you to the concept of Wronskians and all that, and it works very well for a function space that looks like this, where all your functions here are differentiable, okay? At least n-1 times differentiable on an interval, on this particular interval here, okay? All right. So again, so the objective is that right now, the question we are looking at is that we have all this function, f1, f2, all the way to fn. Question is, are they independent or are they not? So we always set up these equations and try to solve for the k1, k2, all the way to kn, right? Okay, so right now, okay, so let's develop a method to do that. So let's start with this assumption first, right? So let's suppose that all these vectors are dependent, all right? So let's for a second, assuming that all these vectors that you have right here, all this vector f1, f2, okay, all the way to fn, they are all dependent, all right? They are dependent. So this is our hypothesis. I want you to pay attention to that. So this is our hypothesis, okay? Assumptions, right? This is our assumption to start with, all right? So this is our assumption to start with. So we are assuming that all these vectors here are dependent, right? They are dependent. That's our hypothesis, our assumptions, which means if you set up these equations, right, the k1, k2, all the ways to kn, they are not all 0. Some of them can be 0, okay, but they are not all 0 because they're dependent, all right? Dependent means not independent, all right? So this k1, k2, kn, they are not necessarily all 0. They are not necessarily all 0, okay? So we don't know which one is 0, which one is not, but they are not all 0. Because if they are all 0, then they are independent, right? So we are saying that they are dependent, so they are not all 0. Okay, so take this equation. Let me just copy and paste this equation here, and let's take the derivative. The objective is to, even though this is one equation, but the objective is to create a system of equations by taking derivative, okay? So this is what I meant when I say that we are going to create a system in an artificial way. So let's take the derivative on the left-hand side. Let's copy and paste this equation here first, and then we take the derivative on the left-hand side. You will get k1 f1 prime, k2 f2 prime, all the way to kn fn prime, and then this will be still 0. So you take the first derivative, place it here. Take the second derivative, place it here. Okay, so the second derivative will be k1 f1 double prime, so on and so forth. And all the way to here, you are taking the n-1 derivative. So you will have k1 f1 to the derivative n-1 times, so on and so forth, all the way here. So the reason why we're doing that is that now we have n equations. Okay, so we have n equations, right? So we have n equations. Okay, so this is equation 0. This is equation 1 all the way to equation n-1. So you have n equations. And we'll also have n unknown. K1, K2, all the way to Kn. We have n equation and n unknown. This is good because if you write as a matrix form, This is going to be a square matrix of size n by n. This is going to be a n by 1 matrix, and this is going to be an n by 1 matrix. Get the typo here, dot, dot, dot should go here. But the key thing is we have this, okay? So now, okay, so we artificially create an equation and an unknown. Okay, so don't forget, what is our assumption here? Our assumption here is that they are dependent, which means all the k1 here, they are not all 0. So I am saying, if you look at this thing here, this is like a system that kind of looks like AX equals to 0, right? N by n matrix, n by 1 matrix, n by 1 matrix. Now I'm claiming that from our hypothesis, the determinant of this matrix here, okay, the determinant for this matrix here, I'm claiming that this determinant has to be 0. Okay, all right, so for all x, so this is not number, by the way, these are all function, right? So if you substitute x into it, these are all become numbers. But before you substitute the x into it, these are function of x. These are all function of x. But if you substitute x value into here, for whatever x value that you substitute inside, this determinant here, okay, this determinant here has to be 0. Do you know why? Do you know why this determinant here has to be 0? Okay, it is because of our hypothesis. This is the first thing that we start with. We start with by assuming that this f1 all the way to fn, they are dependent. So all this k1, k2, and kn are not all 0. So this thing here, the determinant better to be 0. Reason is very simple, because if that's not the case, which means the determinant is not 0, that will imply this matrix is invertible. So if this matrix is invertible, this system will have a solution that looks like this, and the solution for this is 0, which means that in that case, if your determinant is not equal to 0, your k1, k2, all the way to kn has to be 0. But that's not the case, because our assumption is that they are dependent. So k1, k2, kn, they are not all 0. So you better make sure that this case does not happen. Okay, so we will have to end up with the determinant for this will have to be 0. So the determinant for this coefficient matrix here has a name. It's called the Wronskian. So the Wronskian of the functions depends on x, right? Because these are functions, right? So the Wronskian of the functions is basically the determinant for this coefficient matrix. So this is the coefficient matrix. The determinant for this coefficient matrix is known as the Wronskian. Okay, so let's regroup. What do we have? What have we shown so far? Okay, with this new terminology, what have we shown is that if we start with the vectors being dependent, then the Wronskian must be 0 for all x. Okay, the Wronskian must be 0. The Wronskian is the determinant for this. All right, so I'm using vertical line here. So if this is not clear, don't get yourself confused. This is not a matrix. This is the determinant. If you don't like these notations, you can also use these notations. So the Wronskian is the determinant for this coefficient matrix. And what we have shown is that if you start with this functions being dependent, then the Wronskian is not equal to 0 for all x. So this is something that we obtain. Okay, so I'm going to talk about some of you have seen this before, and in our homework we also have done this before. This is called contrapositive. So contrapositive, okay, of a statement of the form if P then Q, okay, is if not Q then not P. So you negate this, okay, if not Q then not P. This is known as the contrapositive for this statement. In logics, these two statements, they are equivalent. If P then Q is the same as saying that if not Q then not P. Okay, all right, so if P then Q is equivalent to saying that if not Q then not P. So for example, if it is raining, then I will get wet. It's logically equivalent to saying if I do not get wet, then it is not raining. Okay, so if person A is a U.S. president, then person A is a natural born U.S. citizen. U.S. citizen can be natural born or it can be naturalized, right? So you don't have to be born here. You can get your permanent residency, blah, 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 go through all the legal stuff, you can be naturalized as a U.S. citizen. But we're not talking about that. If you are not born in the United States, then you cannot be U.S. president. You can be a governor. You can be governor of California, because Arnold Schwarzenegger was governor of California. He wasn't born here, right? But he cannot be a U.S. president. So let's look at the statement. If a person A is a U.S. president, then A must be a natural-born U.S. citizen. So because Arnold Schwarzenegger is not a natural-born U.S. citizen, so he can never be a U.S. president. That is a contrapositive. That's a contrapositive. If not this, then not this. Okay? All right. So don't get yourself confused with something that we call the converse, right? The converse means you're reading it backward. If P then Q, you read it backward, that's called the converse. That is not the case. That is not equivalent. When you say if P then Q, it's not the same as saying if Q then P. All of you know this because usually this is just one way. This is just one way direction. Usually, I mean, all of you know it. When you have a crush, you say, I love you, but usually the person will say, I'm getting a restraining order. The person don't love you back. So reading it backward is not true. That's not contrapositive. Okay? All right? If you have I love you and I love you too, that's if and only if. Okay? That's very rare. Okay? So most of the time it's one direction and you can't read it backwards. Okay? That's not good. But we are not saying reading backward. That's reading backward is called converse, but we're not talking about that. We're talking about concept called contrapositive. Okay, so contrapositive means if P then Q, then if not Q, then not P. Okay, so let's come back to this statement. This is some things that we have. This is the things that we have shown. Okay, if these vectors are dependent, the Wronskian here, the determinant is 0. This is usually not very useful. The things that we want to be, the theorem that we usually use is the contrapositive version of it. This is the contrapositive version of it. So let's take a look. You negate this. So if the Wronskian is not equal to 0 for some x, okay, so here the Wronskian is equal to 0 for all x. So you negate that, okay? Negation. If you negate that, that means the Wronskian is not equal to 0 for some x. Then you negate this, then these functions here are not dependent. Not dependent means they are independent. So what I've just shown you is this, but let's take the contrapositive, and this is the one that's useful for us. This is the one that's useful for us, and that's a theorem right here. If you have a function that is differentiable, and the Wronskian of this function are not identically 0, which means that they are not 0 for some x, so they are not all completely 0, then the functions here are linearly independent. So Wronskian not equal to 0 for some x, okay, is already enough to imply that all these vectors here, all these functions here, are linearly independent. Okay, so this is a useful directions. All right, we didn't prove it that way. We proved this and take the contrapositive. All right. Okay, so I'm also trying to explain what contrapositive is. This is something that if you are computer science, you should have seen it before. Okay, so let's look at how we apply them. It's pretty straightforward. So we have this function, f1 is ex, f2 is e2x. Okay, so let's construct the Wronskian. So Wronskian, sometimes people write like this. Sometimes people just lazy and write like this. Okay, so this is the lazy version. Okay, so the Wronskian is defined as the determinant of f1 and then f1 prime. Okay, f2 and then f2 prime. Okay, so let's do that. So I hope you see this, right? So Wronskian is defined like this. f1, you put the function f1 in the column and keep taking the derivative down the column. Move to f2, take the derivative down the column. All the way to fn, take the derivative down the column. So here we don't have so many functions. We only have 2 functions, f1 and f2. So take the f1, take the derivative down the column. Okay, so you have f1, f1 prime, f2, f2 prime. Okay, all right. So taking the derivative of ex is ex. Taking the derivative of e2x is 2e2x. So take the determinant. You realize that determinant is e3x. E3x is like this. It never equal to 0 for all x. It never equal to 0. Therefore, by the theorem, we know that this function here and this function here This is just a notation for a function that is differentiable infinite many times, okay? You can differentiate EX infinite many times. We don't have problem with that. So this shows that these two functions here are independent. They have no relationship with each other whatsoever, even though they look quite the same, but they are not, okay? All right, so they are not. So they are independent. You cannot write one as a linear combination of another one, okay? That's how we use Wronskian. So for example, how about this function x and sine x? Is sine x related to x somehow? Well, let's put the function f1 here, okay, and take the derivative. Let's look at the function f2 here, take the derivative, find the determinant. Okay, find the determinant. That's called the Wronskian. All right, that's called the Wronskian. So compute the determinants, you have this. Is it positive or is it negative? We can't tell because it's not as simple as the one that we have seen just now. It's not as simple as this. It is something weird, but our theorem is very powerful. Look at the theorem. Okay, the theorem here, like you just make sure that the Wronskian is not equal to 0 for some x. Okay, for some x is not equal to 0, that is already enough to show that we have independence. All right, so just find one of the things that is not equal to 0. So substitute one of the x value, so let's say pi over 2. Just substitute one of the value and show that, oops, this is pi over 2. So it's not equal to 0. So therefore, the theorem will say that this function here, they are indeed independent. That's how we use Wronskian. So you use Wronskian to show that those vectors are in independence. If you manage to show that the determinant of the coefficient matrix, which is called the Wronskians, are not identically 0. Not identically 0 means that at some point it is not 0. Okay, right? So if you don't like these versions, you can just look at these versions. Okay, right? So you'll be like Wronskian not equal to 0 for some x. That means the vectors here are linearly independent. Okay, that's the way how you use Wronskian. All right, this concludes our discussion on linear independence. And the next concept we're going to look at is the concept of basis. So recall that the linear independence gives us an idea on redundancy, and the linear combination and span give us an idea on reachability. So what happens when you have a set of vectors that span a vector space and there is no redundancy, which means that all the vectors are linearly independent, then those vectors will form a basis. So basis is kind of like an optimum collections of vectors that will span the space and there's no redundancy in it. So we're going to look at all this concept in the next video. So I will see you there.